Hello everyone, I'm Martin Black and I would like to welcome you to the presentation on the topic Quantum State Preparation and Measurement using Liquid Crystal and Deep Learning. Today I will discuss the first precise polarization manipulation using twisted nematic liquid crystals. This technique leads to the vibration-free and rapid switching of polarization to speed up the polarization transformation in complex quantum sources and circuits. Beside the display technology, the polarization degree of freedom and its precise manipulation brings advantages in various fields. In biomedical microscopy, polarization-resolved excitation and detection is used to enhance resolution or visualize anisotropic elements like membranes or fibers. In microscopy, polarization-sensitive excitation and detection improve the resolution and specificity of the samples. In optical communication, polarization degree of freedom for encoding and multiplexing improving communication capacity of the channel. The liquid crystal display is composed of liquid crystal cell surrounded by polarizer, protective layers, and mirrors. The liquid crystals inside the cell take a twisted shape defined by unequally oriented alignment layers. When voltage is applied to the electrodes, crystals change the Thiele angles and thus the output polarization state is changed. Single cell does not reach a high enough phase delay. Therefore, we utilize 3 liquid crystal cells mounted on the printed circuit board. The device is easy to use due to all necessary calibration stored in EEPROM and USB communication with the computer. Documentation is available on my GitHub. Firstly, we used the liquid crystal device for polarization state preparation. Here the polarization states are depicted in the two-dimensional projection of the Bloch sphere. To demonstrate the ability to prepare an arbitrary polarization state aside from the 6 Pauli basis states, we prepared 120 states equally distributed on the Bloch sphere. All of these states were prepared with a fidelity of 99.9%. Fidelity is a figure of merit that describes how similar the target and prepared polarization states are. It takes values from 1 for the same states and 0 to the orthogonal one. Because of the absence of a precise analytical model, we utilize the Genelig-Reich algorithm to speed up the searching process of target voltages for target polarization projections. Beyond the pure states, the time averaging can be used to prepare the depolarized or mixed states. In this task, we prepared a polarization state with the length of the Stokes vector of 0.03. When the state is fully depolarized, this figure of merit is 0. Until now, I've been talking about polarization state preparation. So let's move to the polarization state measurement. Here the polarization state is prepared by the polarizer, quarter wave plate and half wave plate. This state passes through the twisted nematic liquid crystal device, which performs the polarization projection in combination with the polarization beam splitter. Here we go through all 6 Pauli projections for which the combination of the voltages was found in the previous calibration step. To obtain the reconstruct polarization state, we use the maximum likelihood algorithm. We also perform the reconstruction of the same states by the commonly used waveplate methods with fully comparable results. Both methods reached the fidelity higher than 99.9%. These results certify the liquid crystal device for use instead of any waveplate tomography stages in any experiment. In quantum communication or information processing, The strongly correlated pairs of photons characterization and manipulation is also indispensable. But with increasing number of modes, the number of necessary projection is increasing rapidly. We use the liquid crystal device for free-mode entangled state reconstruction to demonstrate that the liquid crystal device is also suitable for this single photon application. First, we reconstruct the free-mode entangled Greenberg-Horn-Zeilinger state using the three pairs of waveplates, and then a liquid crystal device. The fidelity of vertical state measured using the liquid crystal device and the waveplate polarimeter reach 97%, limited primarily by the processor alignment repeatability. As I mentioned before, it is necessary to cycle through the set of the projection in the polarization state measurement. Nevertheless, the sequence doesn't matter. Therefore, we measured the switching times and used Hoshak et al. Optimization method to choose the best sequence. This method is not only limited to the time-saving application. It can also be applied to the integrated chips and optimization of the heat load. To find more, check the reference on the right. The analysis is faster than an order of magnitude in the single qubit case when the twisted nematic liquid crystal device is used. Moreover, in the multi-qubit case, the acceleration is more significant and the number of required projection increasing exponentially with the number of qubits. On the right, the increasing saved time is plotted as a function of the number of the qubits. For all of these tasks, it would be beneficial to have a precise model of the liquid crystal device to predict the voltages for target projections easily. However, the analytical model assumes that the till and twist angles are constant through the whole cell. Nevertheless, in the actual cell, they vary. This limits the accuracy of this analytical model roughly to the fidelity of 91% for a single cell pass. Moreover, this model can't be inverted and it predicts only output polarization for the applied voltage. Therefore, we developed artificial intelligence model. Using the neural network, the polarization state prediction accuracy of the whole free cell device for given voltages is 99.9%, and in the inverse task of predicting the target voltages reaches fidelity 99.8%. To demonstrate it, we used this neural network model to predict voltages to plot the logo of our university on the blocksphere. Then we applied these voltages to the liquid crystal device and measured the output polarization states. To sum up, twisted nematic liquid crystal allows fast and accurate preparation and analysis of polarization state. The results are consistent with the state-of-the-art waveplate method but faster and vibration-free. Recently, two papers were published. In the first one, we present the first precise polarization manipulation with twisted nematic liquid crystals. These vibration-free, voltage-driven elements allow fast polarization transformation in quantum circuits and entangled sources. The second one shows the first bidirectional control of quantum devices invariant on the type and number of classical control signals demonstrated on a liquid crystal polarization control. Here, the unlimited control of polarization quantum states, devices, and measurements is achieved by neural networks. This approach is expandable to other systems, such as optical chip circuits and others. The results open the way to continuous manipulation of quantum information, even in systems with complicated response to external control signals. Thank you for your attention. Check out my Twitter, GitHub, or our group webpage if you are interested. And if there are any questions, please feel free to ask.